Now, all that's super, and I hope you followed it, but how do we know? Well, now we're going to revert back to something you learned in A-level. And that is that transition metal complexes are most often coloured. They're not all coloured, but awful lot of them are coloured. And the reason for that is because you have electrons moving from one d orbital to another d orbital when you shine light on them. When you do spectroscopy on those, you get electrons going from the ground state to the excited state. Well, of course, if we think about octahedral or tetrahedral, we have these energy gaps between the splittings, and those energy differences usually correspond to visible light. So if we take an octahedral complex that's got an electron in one of the T2G orbitals, we shine exactly the right amount of light onto that. It will absorb a photon, it will pop on up to the higher energy orbital, and the photon, the energy of that photon, the wavelength of the light of that photon is usually visible light. Now we can take spectra of these, and this is just a fast picture taken of a octahedral complex. What I'm showing here is we have wavelength going along here, absorption going up there. Most of the light isn't absorbed, but there are certain wavelengths at which light will be absorbed, visible light will be absorbed, and you can see it goes up to a peak up here. That is the highest absorption of the light. And being able to do visible spectroscopy on these coloured complexes of transition metals makes it very easy to get some nice data to try to explain everything. Now, just to give you a few examples, looking at our chromium complexes that we had here. So chromium cyanide, very high delta oct. This is going to be a would have very high splitting between the orbitals. Ammonia as the ligand, that's towards the right of the spectrochemical scale compared to cyanide, so a smaller delta oct. Oxygen even more to the right, so a smaller delta oct. Fluoride even more to the right, 15 delta oct. So the size of the splitting goes down as we go down here. The energy goes down as we go down here. Okay. Now, what we do with our spectroscopy is we throw in a solution into our machine and we measure the absorbance, and this lambda, this wavelength, would be that highest energy absorbance. Okay, so here are the lambda values observed for what we see here. And of course we see lambda, which is wavelength, is increasing as we go here. And remember, lambda wavelength is inversely proportional to energy. So the higher energy gives us the lower wavelength. Okay. Now we can match up wavelength to color using the little color wheel, because of course in a very, very rough sense, and this is an extremely simplistic definition, the color that you see is the color that is not absorbed by a substance. Okay, and of course what we're measuring here is we're measuring the color absorbed. And it's, as I said, not as simplistic as that, but I hope you've seen the color wheel, which is essentially that the color that you see go across the color wheel, and that's the color that was absorbed. So for example, if we start off with our cyanide complex, we see that it's a green color. Okay, so we're going to see a greeny color here, which means that we are absorbing a purple color down here. Purple color, of course, is the highest energy, or violet is the highest energy of the visible spectrum, and so we see a nice low wavelength, high energy wavelength being absorbed. Okay, we see green because it absorbed the purple, it absorbed the high energy purple photons. Go to the ammonia, and the ammonia complex looks kind of yellow. So we're seeing yellowy up here, go across it, and it absorbs the blue. Okay, now of course blue is less energy than purple, less energy than violet in our electromagnetic spectrum, and we see that it's less energy, it's got the higher wavelength. Okay, next one, chromium, hexaquo chromium 3 is violet, so we're seeing here and it's absorbing there. Okay, so we've got the absorbance in this sort of greeny yellow area. That's why I've put that for the wavelength. That absorbance is a higher wavelength, lower energy than the purple and the blue. And then finally, this hexafluorochromium 3, or actually hexafluorochromate 3, right, it looks blue-green. Well, blue-green is here, so this is the color that we see, which means it's absorbing red light. Red light is, of course, the lowest energy of the visible spectrum, which means it has the highest wavelength. Okay, so we see the different colors of transition metal complexes because electrons are moving from one d orbital to another d orbital. The energy splitting is, of course, the delta oct or the delta tet, and so the larger the delta oct, the more energy the electron has to have to go from the lower energy to the higher energy. So what we see is that the higher ligands in the spectrochemical series, the stronger field ligands, are going to have a bigger delta oct, which means that the energy that they absorb is higher energy, lower wavelength. The wavelength, the energy difference, corresponds to wavelengths in the visible spectrum. So we see these pretty colors of transition metal complexes. Thought it might be worth finishing off this particular set of movies by going back and looking at a couple of the pairs of isomers that we saw earlier and looking at how you can tell between these based on the ligands and thus the wavelength absorbed. So here we have the ionization isomer examples where we had the hexaaquochromium 3, replace then one of the waters by one of the secondary coordination sphere chlorides. Now we've got a chloride here bound, that water goes into the secondary coordination sphere. So here we have pentaaquochlorochromium 3. Okay, first complex is violet. Now that means that we see down here in the violet, so it's absorbing a photon up here in the sort of the greeny yellow. Okay, then we replace one of these waters by the weaker field chloride, and the color goes to blue-green. So we see here in the bluey green area, which means that it absorbed a red photon. So this absorbs a red photon, this absorbs a sort of yellow-green photon. The yellow-green photon is higher energy than the red photon because delta oct is bigger here than here because we're replacing a water ligand with a chloride ligand. Chloride is a weaker field, so delta oct gets smaller. Because delta oct gets smaller, the photon that is absorbed gets smaller, so the color changes. Another classically important one, linkage isomers, whether you have nitrogen coordinated of the nitrite or oxygen coordinated of the nitrite. Very, very significant here in the history of coordination complexes. Alfred Werner saw these and actually explained the differences. When you have nitrogen coordinating, it's yellow. When you have oxygen coordinating, it's red. Let's look at this on our color wheel. The first one we see yellow, which means that we're absorbing a blue photon. The second one we see red in a nice way, which means that we're absorbing this lighter blue photon. Okay, lower energy absorbance here than here, lower energy absorbance when it's oxygen coordinated than when it's nitrogen coordinated, because of course nitrogen ligands have a stronger field than oxygen ligands. Stronger field, bigger delta oct, higher energy photon absorbed, different color. Hope you enjoyed this. We went massively into A-level or degree, first year degree material here because I didn't like the A-level stuff. I'm so sorry. I doubt there'll ever be an A-level examiner listening to this, but really what you do with transition metals is boring. This is much more fun, going deeply into this.